So I think most of us know Faruk. Faruk Gulban is working for Brain Innovation, the company behind Brain Voyager. He is a good friend and long-term collaborator with myself. Today he will talk about Meso-Vessel imaging with 7 Tesla, linking anatomy and function in living humans. And I'm specifically excited about that because it's using a 3D EPI protocol that is very robust, and we have it on both of our 70 scanners in Brigham Women and also in Bay 2 at Martino Center. And I'm doing it and running it almost on any participant just as an add-on for fMRI. But there are many other cool applications, and maybe Faruk will show some of those. Please, Faruk.
Okay, so thanks for the introduction, Renzo. And I just want to say that I got a bit sick yesterday, so if I make strange noises, please forgive me. I will cut it after the recording. Okay, so yes, I work in the Brain Innovation. I'm also affiliated with the Maastricht University. Just quick shout outs. I work at mesoscopic MRI below 0.4 millimeter isotropic resolution these days. And I develop together with Renzo the analysis tools in Laney. Also, I have a YouTube channel that I share and disseminate our expertise on these very niche topics on YouTube by doing video tutorials. And specifically, this talk was actually given 2 weeks ago at Italy, Erice, in a really nice conference called ISMRBF. But since Renzo said that we had an opening, I just stepped in and said that, yeah, I can repeat this talk. So I actually don't like to repeat my talks, but this is an exception. Okay, so let's jump in. On the left-hand side, hopefully through your Zoom, you are seeing at a good enough refresh rate that there is a piece of brain there, and there is in the middle, there is this dark thing that is kind of pulsating or fluctuating, right? You can, I hope, see that little thing. So if you just look around a bit, you might even see that maybe the gray matter is changing its intensity a little bit. Of course, I assume you know where is gray matter and white matter here. And by the way, this is a finger tapping experiment that Renzo did many years ago at NIH, collecting some high resolution 0.8 millimeter in plane and 1.3 millimeter in slice direction fMRI data. And we are just looking at a finger tapping result. Like activation to the finger tapping. And basically, like without using any statistics or anything, I can show you that there is something going on, periodic, right? This was a 30-second on, 30-second off task. And once you look around this image, you might even notice that in some areas, for instance, here or there is these dark spots that are also kind of pulsating in this view. Well, this is basically fMRI story. That is, I'm going to summarize here and inspired by Bob Turner's 2002 paper. So what's going on here is the following. So the person is doing finger tapping. We are looking at the motor cortex and some of the sensory cortex in the vicinity. There is some neuronal activity in the gray matter, like in this cube, you can see. And there is this all plumbing system connected to it that is supplying some oxygenated blood there and moving stuff around for the neurons to thrive and do their job. And what is happening is that when the neurons are very active, the body is sending lots of blood there, oxygenated blood in the arteries, flood the arteries, and then they, of course, through the capillaries, move towards the veins. And from the veins, it goes up, drains towards the pile surface. From the pile surface, it connects to larger pile veins and later bigger veins to the sinuses. I didn't write it here, but you can imagine that there's the artery and the vein kind of toy diagram here. The artery brings the blood in the capillaries, then the veins collect and go back to the heart. So this is the context that we are in. And this is why I believe the study of the geometry of the vessels are very important for fMRI. So I almost sometimes find that it is strange that I need to say this, but interacting with like fMRI researchers, I come to appreciate that many people actually do not think about the geometry of the vessels enough, but analyze fMRI data. But the fMRI data, all there is actually about the vessels and how the oxygenation changes in the vessels, maybe how they dilate and so forth. So this is why study of the vessels are extremely important for anyone doing fMRI research. And it's not what I'm saying, like Bob Turner said it years ago, and also Ogawa and others, like all these papers are written in that way. So now a few definitions before I load the other stuff. in this talk, I am going to talk about our contributions in the recent years. But what I'm doing is basically I'm pushing the Meso-Vessel imaging or the vascular imaging of the human brain to a kind of an unexplored regime. And the situation is that we have single slice and very high resolution imaging of the human brain and vessels. And we have lower resolution but whole brain imaging of the human brain, human vessels. But I think we need to push towards this mesoscopic regime, which is within reach with ultra high field MRI. And we can study some vascular geometry there. So basically I am pushing to the mesoscopic scale, and then also trying to accomplish whole brain imaging at the same time. So that's my constraint right now. In there, I found the following definition to be useful. So if you think of the vascular axis from the heart to the capillaries, we can maybe denote the microscopic vessels as microvessels and macroscopic vessels that we can see by eye when we open up the skull as macro. These are above 0.5 millimeter in diameter. And everything in between I call the mesoscopic vessels or meso-vessels. And there's a reason for it, because there is a special regime where the space characteristics of these vessels change in that mesoscopic regime. I will come to it in the next slide. Okay, so just to say that I am not the first person to push in these dimensions, thinking of the macro, meso, micro vessels. You can see that in 1514, a person called Vesalius published a book that says the complete account of arteries and veins in the human body. So based on this, basically none of us has any business to do. These are all completed knowledge, right? So I'm not saying I do anything new here. Maybe like the new part is that being able to do these type of things in living humans. Then we can, of course, see, just to fill in some of the gaps in the history quickly, the very famous paper of Duvernoy. I am probably mispronouncing this French name. So he shows a very nice hand-drawn picture of the human cortical vessels. These are, of course, based on real data that they use gel injections, and the scientific illustrator kind of looked at this data and drew it. Then there is another actually interesting work from Salomon from 1971 that only injected gelatinous ink inside the arteries and did these photographs of the, I think, 1 centimeter thick slices of the human brain to show the arteries and how they kind of orient inside the gray matter and so forth. And of course, again, the Duvernoy showing the microscopic part. So these are all kind of the different regimes. So now the interesting thing about the mesoscopic vessels is the following. This is a special regime. Lots of interesting geometric stuff happens. For instance, when we look at the cortical surface from the top, we can see all these rivers. Basically, these are the very dark ones are veins here. You can see that they are branching, going around the surface of the cortex. If we peel away some of the layers of the superficial cortex, we can see that these are becoming like basically pipes, dots that are penetrating perpendicularly the cortex. So you can see that the spatial geometry and how things are aligned kind of changes. And just inside the gray matter, let's say the mid thickness surface, you expect to see these very regular dotted geometry. If we look at it from the side, our cortical layers, you can see that, well, many people think when they think of the cortical layers, they think of the neurons or the myelination. But actually, the angioarchitecture changes across layers as well. There's an angioarchitectonic layering of the cortex as well. And here you can see that there are some parts that the capillaries are denser and the other parts that are less dense, right? So we need to also think of that. And I think not enough people are kind of thinking in this way these days. And the other interesting geometric part is that the veins that are penetrating through the cortex, I mean, I say here veins, arteries a bit mixed, but hopefully it will clear up soon. I mean like vessels, actually. In this specific picture, it's a vein. You can see that the vein is kind of draining, I guess, from the white matter. Then there's the white matter, gray matter boundary. It is still draining laterally within the gray matter, even though it's coming from the white matter, right? It's still draining and going up. And its catchment basin is this probably conical shape, if you think of it in 3D. So basically the body is solving some, like a material delivery problem, right? It's minimizing some sort of cost, arranging itself in these geometric shapes to kind of optimally deliver whatever it is delivering to these neurons and capillaries and so forth. But this is exactly why the mesoscopic regime is interesting, because there's like all these different aspects are kind of going on there, like laminar, this conical catchment basin, this distribution of the penetrating veins, and also in the pile surface, all these rivers and branching of the veins. Okay, so given that you are somewhat convinced that these study of the geometry of the veins and arteries is relevant for us doing human brain imaging. So this is what we have achieved recently. So we have used multi-shot, multi-echo 3D EPI implementation from Rüdiger Sternberg, our collaborator. And basically we spent several months, maybe a year, optimizing this and achieved 0.35 millimeter whole brain imaging. And this is below, I believe, again, I wrote it. It's 6 minutes and 44 seconds, but this is not a big, this can be optimized further. Like, don't get hang on to it. Like we can go to 4 minutes, 2 minutes. Like, it just depends on how you set up your acceleration and so forth. And also how fast your reconstruction PC is. They can crash the scanner if you go too fast. But here we also did, instead of single echo, multi-echo. And this was for a reason, because we had this anatomical mindset. We wanted to study the geometry of the vasculature in living human brains. We wanted to keep the readout as short as possible so that we are not so much affected by the spatial geometric distortions that you would end up having if you think of a very large readout, EPI readout, for instance, that is used in fMRI imaging. Anyway, like some parameters here, we can discuss more on it in the future. But you can see that we have a very luxurious coverage, actually. We can really cover the whole 2 hemispheres plus the cerebellum, I would say, if you position it correctly. And with a bit of intensity projection, you can see that many of the vascular details are just popping up in this data. This is a very rich data set. And you can even see that in a single slice, you can see those penetrating veins as like single dots. Okay, so now, of course, this might not be so convincing for many of you. I just showed you one hand-picked image. Therefore, I'm going to now show you and try to convince you that this is something that works across people and across subjects and runs and so forth. And one, of course, issue in doing this imaging is that, oh, what about the head motion? This is like first thing everyone asks, right? Oh, can you even get like anything meaningful at 0.35 millimeter isotropic resolution? How can it be that a person lies still inside the scanner 6-7 minutes and lies still below 0.35 millimeter like a motion, right? Well, now I'm going to argue about this. So you can see the run 1, run 2, run 3, run 4. These are all the echo average. So I'm just simplifying across echoes and just showing you the echo average of these 3 echoes. And I'm now going back and forth between 4 different runs we had. So this is more or less like a half an hour worth of data. And you can see that indeed, for instance, look at subject 7 between run 4 and run 3. There is a very big head motion, right? Very big, like centimeters big. Whereas the other subjects were pretty good. Okay, like there's this head motion, but this is across runs or in between runs head motion. And what we specifically instructed the subjects was that, hey, like try to stay still as much as possible within the run, right? But in between the runs, if you need to move, be comfortable. Like some people kind of take an issue with it, but I can tell you that in my experience, this like drastically improves the data quality without using, of course, prospective motion correction methods. Like I am in a regime that I'm not using prospective motion correction. If you use, the story might be different. But I don't have any prospective motion correction. And what I need to do for getting good data is to make people as comfortable as possible. This is like the utmost priority. And once it is achieved, now let's see how the data quality changes across runs. So now what I'm showing here is that the motion corrected runs, so these are 4 runs again across each subject, and I just zoomed into some area to show you the details. And I did a little bit of maximum minimum intensity projection to kind of highlight the fine details of the vessels here. So now let's see, run 1, run 2, 3, 4. Do you see any big difference between, let's say, run 3 and 4 in subject 7 after the motion correction? I would say absolutely not. like the details are just there, visible. So which means that if you can deal with this within run head motion by making people comfortable for 7 minutes and letting them move if needed in between the runs, you will get very good data. And of course, some people say, like, how can it be that you see like all these details at 0.35 millimeter? Well, my point is that like the details are just there. So whatever we were thinking that blocked us from going to 0.35 millimeter, let's say, it was not the correct thinking. Like people can stay still, and through all these acquisitions and collecting the case space data and reconstructing, we are fine. We are getting the details correctly. And the simple motion correction works. So now just a note, this 3D EPI multi-shot, multi-echo thing didn't appear out of thin air. This was my research line since like 5 years. And I started first working on 3D multi-echo GRE. That is what I guess anyone would start from to look at these anatomical details, especially T2 star imaging. And then slowly we moved towards the 3D EPI as an acceleration method, basically, to like the first data that I'm showing in this slice here on the left-hand side, the multi-echo GRE, this is like a 7 hours of data for one subject, multi-session, all aligned together and so forth. You can see the details below. If needed, take a screenshot and look for the link. But then building on top of it, we use the 3D EPI as an acceleration method to basically, instead of the 7 hours, right, how can we do the same in 7 minutes? That was basically the story. And I believe we achieved it. One of you might pay attention to this 3D EPI that is not multi-echo. This, I think, if I remember correctly, was a 4-minute version of our imaging. And we could have done actually in 2 minutes as well. But then, as I said, the reconstruction PC was crashing because you just stack up many 2-minute runs, but it takes like 6 minutes to reconstruct. We are not using offline reconstruction. I just didn't want to do that. And if you stack up too many of these 2-minute runs, it will crash the like recon PC and you need to reboot the scanner. So it's like I put it there just to give you the idea that the regime that we are at right now, this 3D multi-echo EPI 7 minutes, I don't think this is like the end of it. We can optimize it way further. It's just a bit of like all the other components of the scanners that needs to improve and we can move forward. Anyway, okay, so now having like getting good data is not good enough to me. This is really like maybe less than half of the work. I can just show you some nice brain images, right? You look at it, you appreciate it, and I get lots of likes on social media and so forth, but then what is the use of it? Well, that is exactly the other part of my research, particularly in the company at Brain Innovation, developing new algorithms to analyze this data and so forth. So how do we bridge this gap that we have the data? How do we extract information out of it? So to do this is a complicated task because there is not like a path that is open that one can follow. So you need to experiment with things. But I found the following thinking very critical and very important. And that is written in Duvernoy's 1999 textbook. He opens up his chapter on the cortical vessels by saying that there are actually, like, anyone who studies the cortical vessels should first recognize that there are 3 classes of cortical vessels that you can study their geometries. First is leptomeningeal, second is spiral, and intracortical aspects. So what is the leptomeningeal aspect of? Some people might not be familiar with this term. I wasn't, then I got familiar. So when you look at the brain, so there is the bone. I hope many of you know about the sinuses, this sagittal sinus, this big vein that is on the top and in between the hemispheres. And then there's a membrane just below it. That's the arachnoid membrane. And like below the arachnoid membrane, you have the pyometer and the subarachnoid space. And this is a space where big veins and arteries kind of hang around there. And even this like arachnoid membrane. So that space is called leptomeninges, as I learned. And basically, like all these kind of vessels that are not on the pile surface of the cortex, but from pile surface and to the arachnoid membrane, I call the leptomen, or Duvernoy calls the leptomeningeal vessels. Then we have the pile arteries and veins that are way smaller, of course, that are kind of stuck on the surface of the gray matter, and they dive in. The moment they dive into the cortex, they become the intracortical vessels. Okay, so thinking of this, I did the following tweaking first. So I get a brain mask, just a simple brain extraction, and I edited this mask in a way that I get a nice leptomeningeal segmentation out of it. And here you can see that whatever I color as red kind of encapsulates the gray matter and white matter, right? But it is going up until the arachnoid membrane, let's say. And that I call the leptomeningeal mask. It's a bit like more tweaked, optimized brain extraction, basically. Think of it like that. Okay, so with that mask, you do the following visual. So this is actually just the T2 star weighted data. I did get the reciprocal of the T2 star weighted data so that the dark veins in the T2 star weighted data become bright. And it is more advantageous when you do these volume renderings to have like interesting things on the brighter parts of the image. So this is a 1 divided by T2 star weighted contrast of the brain that is masked by the leptomeningeal mask and rendered using volume rendering in some software. And note that this is not segmentation, like a vessel segmentation dependent, right? All I have to do is this coarse, quite smooth leptomeningeal mask, and by leveraging the T2 star weighted contrast in the right way, I can already start having some insights about the vascular geometry and the arrangement. Oh, just maybe a note before I move further. So this rendering I did specifically to kind of see how well we are matching with regards to the Duvernoy's illustrations that are, let's say, the gold standard for many years now. But now the difference is that this is done a couple of decades ago by, you need a scientific illustrator to do it and lots of hours of research. Whereas on the right-hand side, we can get this image basically using a 7 minute of scanning. Let's say you repeat it twice just to have some redundancy. So like 14 minutes of scanning, let's say, and then processing it in a way that you do the leptomeningeal mask and then render it. And we are already like quite closely there, right? And this we can do in many different living humans. We are not stuck to this like one model brain anymore. And here there are other interesting details. For instance, you can note that I have colored the arteries in red because some of you might think that, oh, these multi-echo, multi-shot 3D EPI images with T2 star weighted signal, do they only show the veins? What about the arteries? Well, they also show the arteries. Arteries are also dark there, and there's a reason for it. That's called the blood motion artifact. I'm not going to go into detail unless if there's a question at the end. But basically, no, like this image that is 0.35 millimeter whole brain T2 star weighted image does not only have veins, it also has arteries in it, but they look dark. And you need to kind of know whether they're arteries or not by following their gross anatomy to see where they connect. But if you do that, you can actually recover some of the arteries. And you can see it with this like red halo here, similar to what Duvernoy did back in the day. Okay, so about the insights of the vascular geometry. So what I found interesting is the following. See, for instance, on the upper row, there is subject 1, left and right hemisphere. When I am looking at the center of this image, let's say this area, on the right hemisphere, there is like a massive vein there that is looping, right? From this temporal cortex to the sagittal part of the brain, middle section, there's this big arm that is forming a big loop. Whereas on the other hemisphere of this subject, that big arm is not there. Whereas I see maybe 2 arms there, 2 veins. Maybe this one is connected here. So this is a very big difference in the geometry of these big veins, leptomeningeal veins, across the hemispheres, right? Now let's have a look at across the subjects. What about between subject 10 and 1 here? Well, the subject 10 now has that big loop on the left hemisphere and not on the right hemisphere. The right hemisphere has a different configuration of the veins, right? So now, looking at it and having this insight, I am wondering how this would affect some of our fMRI analyses, like whatever, call it like resting state connectivity analysis or task-based fMRI analysis and so forth, because those veins are draining all the oxygenated blood, right? Like they are kind of draining, and there might be spots where if the activated area is large enough, we might end up detecting fMRI signal activity in these big arms, because they are draining from the region of the activity. And I'll come back to it later in my talk. So this is not just a speculation. Okay, the other improvement that we did in our talk is to optimize the visualizations a little bit more to, for instance, here you can see that we can go a bit further than the leptomeningeal visualization, and we can carve out some pieces of the brain. For instance, here I took the Heschel's gyrus because vascularly speaking, it's an interesting area. There are very big arteries there, very big veins also, kind of draining away. So we move there, and you can see that we can start seeing the configuration in the pile vasculature there by doing these cutout volume renders. More details are in the paper, of course. And now the third development in visualizing these detailed structures or this information that's available in the data is the intracortical mesovein. So here you can see a middle gray matter surface, just showing the T2 star weighted contrast. So this is literally every vertex as sampling from a single voxel, right? Very dense like this is a very dense mesh. It's not like decimated. And it is sampling just where each exact vertex stays in the voxels and then takes the T2 star value from it. And you can already see that there are all these little dots, right, peppered around in a nice, almost like a regular way. And when we do the inflation of this cortical surface, we can see that they are actually everywhere, all these dots, right, peppered around. These are the intracortical mesoscopic vessels, and I believe they are mostly the veins here because of the T2 star weighted imaging. But this is interesting because we can take this image and now we can look at it across layers. So instead of the middle thickness, I can look at a deep layer, I can look at a superficial layer, and there I can even trace some of these dots from the superficial to deep part. For instance, here you can see that one of these dots kind of disappear when it arrives to the deep layer, but some of them kind of is consistently there. And this matches very well with Duvernoy's classification from vein class 1, 2, 3, 4, 5, and you can see that class 3 goes to the middle cortex, and that's why I here speculated that maybe this little white dot here that is visible at the superficial and the middle layers and not in the deep layer might be an example of a class 3 vein that we captured in vivo, right? And maybe the other one is a 4 or 5. I do not know whether it's 5 because I didn't trace it below the white matter. If you can, of course, you can determine whether it's class 5 or 4. Okay, another way of looking at all this information is that from that dotted inflated brain, you can implement some algorithms, and I am working on this manuscript right now, that converts that map into a Meso-Vessel density map. So you can count how many of those penetrating things per centimeter square there is on the surface. I mean, this is just one subject, so don't take it too seriously, this work in progress. But for instance, you can see that there's a high density of mesoveins in the calcarine sulcus in both hemispheres. Whereas if you compare it with some other measurements like thickness curvature or cell bodies from the big brain data set, that type of like a highlight that is only within the calcarine sulcus doesn't come up in the other measurements. So this might mean that this Meso-Vessel density that we can now reach in vivo might be really something meaningful, like a new contrast, new way of mapping the brain that we can add on top of the other measurements that we already have. But this is, again, like very much work in progress. I don't know how it will turn out. Okay, so now from here, I would like to switch to a more interactive part of my talk. Okay, so what you are seeing right now is a new software that we are developing. This is a part of Laney, but this is a GUI extension of the Laney. So it's called Laney IDA. And I was developing this because I was looking at lots of GRE images. For instance, here you can see this 7-hour-long multi-echo 3D GRE image that is kind of combined together, stitched together, so you can see some of these halos there. But I developed this software to basically look at this data in a fast way that I would like to do. And for instance, here I'm going through the time points, different echoes. I have 6 echoes here, and I can see that around these big arteries, there is this white thingy that is going around, right? And you can see that if I click there, the canonical, like a T2 star decay is not there. Like it sometimes goes up and down, up again, down again, right? So there is something going on. So anyway, like the explanation of what this is actually written in my 2022 paper. This is due to the blood motion artifact that happens in the big arteries. But this is one of the reasons why I developed this software. So now I would like to move to another extension of this software that I realized later that it was actually useful for, and that is in the fMRI context. So now here I am plugging in the Kensho dataset that Renzo recorded when he was in Maastricht a few years ago. So this dataset is basically one participant going through like something crazy, like 50 sessions of fMRI experiment sessions. And in each session, he watches the same movie again. So this is a movie watching task. Also, some sessions were done for finger tapping and checkerboard kind of block design experiments. But basically, this is a lot of data put together at 0.8 millimeter isotropic resolution and whole brain, right? This was the whole push that Renzo did. So now I wanted to look at this data to understand a bit better what's going on in 3D EPI in general. Then I realized that, wait a minute, like one way to kind of understand this data and have a look at it is actually use correlations. And here I started looking at this data, 0.8 millimeter isotropic, whole brain. The auditory kind of areas become active when I'm looking at the correlation. And you can see that the correlation value, if I fix the correlation here, is actually rather high. Like see, it's like 0.8. Then I can look at the visual part of the brain and capture maybe the visual network, maybe a bit lower. I mean, I say network, but actually I'm not a network person, so don't get offended. Like this is just like correlation analysis to me, like fMRI correlations. I say network because many people like to say that. Okay, so there are of course other uses of this little software with real-time voxel-wise correlations, and that is to detect artifacts. This is another thing that we were looking at with Renzo. For instance, look here, there is some bad, nasty artifact, and I can just fix my correlations there and browse the data to see like how that artifact is affecting the rest of my 3D API imaging, right? This was all the mindset. Okay, so now you might be thinking, why the hell is he talking about all this stuff now? Where is the vessels? Where is the like the connection, right? The connection is coming very soon because I realized this. Look, when I click on the sagittal sinus, you can see that it is kind of popping up by itself. All these vessels are kind of rising, because they are doing something by themselves, correlating by themselves, but they are not really so much correlating with the visual cortex, let's say. Like I look at the visual cortex, there's like something else going on there. See, something structured. Or I switch to the auditory cortex. Like there is definitely something specific going on there. That is not just like vessels going up and down. So, okay, now keep this in mind because all this structure and a few results that I extracted from here, now I'm going to switch to visualizing them using some new methods. That's why I wanted to show you all this like Lane-Ida stuff to see like how this is done, this voxel-wise correlation analysis and exploring the data. Just a step back. Now I am showing you these subdural volume renders. These are not leptomeningeal renders because here I decided to include everything below the dura mater, which includes the big sagittal sinus, as you can see here, and both hemispheres here. One looking at from the side, from the top, from the back. This is the 0.35 millimeter T2 star weighted data, how it looks when you do this render. I mean, it's pretty nice, it's fascinating and so forth. I'm going to overlay our registered fMRI data here, 0.8 millimeter or 84 millimeter isotropic Kensho data set that is registered to the 0.35 millimeter whole brain T2 star weighted data. And now I'm showing you the time series average. So this is just the average T2 star weighted image that comes from the fMRI EPI. Now we can go back and forth, and you can see that to a very large extent, this is a good registration, right? Maybe there is a bit of emotion, like not a good registration, but rest of the brain is pretty good registration, I would say. Okay, now I will switch to the fMRI activity, not the anatomical like contrast that I pull from the fMRI data. So here, what you are seeing is the activity to checkerboard and tapping. This was a simple boxcar model that I used to correlate with all the voxels using Lane-Ida. So this is a very simple, like a boxcar modeling, right? There is not even a double gamma HRF. Since it was like 30-second on, 30-second off, it didn't matter so much anyway. And what are we picking up here? You can see that the motor areas are kind of popping up, right? Whatever you see bright is a high correlation. And the visual areas are popping up. But look what else is popping up. What is this guy? This is the sagittal sinus, right? but only the area that comes right after the motor cortex is kind of showing high correlations with the boxcar model. And since the subject was lying down in the scanner and blood was draining in that way from the motor cortex, I think it makes sense that in such a strong like stimulation, checkerboard and finger tapping for 30 seconds, you end up basically detecting fMRI activity even there in the simple design. So now let me switch to the movie watching view that I showed in the Laney Ida a few moments ago. This is the visual cortex correlations. I picked up one voxel from the visual cortex and now showing you from the back. And look, there is this kind of stripe here, right? One stripe, two stripe, and maybe like something going like this. Well, where is it connected to? You can see that there is a big vein that is actually exactly from there, draining towards the sagittal sinus, right? Again, the activity there and how the blood is drained and following the vascular geometry, it kind of makes us understand that this little stripe is probably just a vein that is draining from the neuronal activity site, right? And by the way, this is to me nothing new. Like Bob Turner, like exactly talked about it in 2002. Like this is to me like completely expected. It's just the new part is that now we have the data in vivo to actually like see it immediately, right? Now I'm looking at the auditory cortex, and you can see that there is this kind of lateral activation here, or high correlations. And of course, when I overlay it with the anatomical data, you can see that there's a big vein here exactly along how the auditory cortex is drained in that region here. And if I correlate with the sagittal sinus voxel there, you can see that just from the correlation, like voxel-wise correlation analysis, and one voxel chosen inside the sagittal sinus, I kind of highlighted all these vasculature from the fMRI activity, right? That's like the different part. Okay, now I'm coming to the end. I don't have much more than this. This is one new visual that I've been working on, that is to overlay the mesoveins data at 0.35 millimeter together with the fMRI data using this subdural volume renders. And to do that, I used the red channel to kind of put the fMRI data there. And when I did that, it actually becomes really fascinating, because immediately you see that in the checkerboard and tapping task, there's all this activity, but how this activity in some areas spread, right? It really very nicely follows the veins. Even like maybe the extent of this activity on this outer shell of the brain back here kind of follows the arms of the vein here. So this is all like why the geometry of the veins kind of matter in the way I think we interpret the fMRI data. However, I would like to make an exclamation point here. This is like a very simple on-off task, right? I didn't look at some contrast now that is complicated, like or PRF mapping and some like complicated categories, 3-4 different categories mapping that. So in that situation, I don't exactly know how the geometry of the veins will affect at the end the map that we are seeing, but I can imagine that they will have some effect, and this is some work that will be done in time. This is simple on-off task. Now I'm switching to the movie watching, again the visual cortex. You can see that all these bright spots that are popping up here, maybe there, they are kind of nicely following the veins. This is the auditory cortex activity correlations. You can see that the activity is spread along this line, exactly along the big vein there, and so forth. Okay, now, to me, we are at a very exciting time of this type of research, and there are many directions to go, almost like too many. I would like to show you some of the directions that I am going through together with my collaborators. First is from Rudy and Matthias. They are implementing prospective motion correction methods just to make these mesoveins imaging more applicable in clinical populations, so that we spend 6-7 minutes, right? And even like with the people that move a lot, we still get good data. Of course, this is not the case. Like if you move inside those 7 minutes a lot, you will not get good data. What I was telling at the beginning of my talk was instructing healthy subjects, like how to behave. So they are working on it. They get some really excellent data, I would say. But this is work in progress. I think they even submitted to ISMRM, so watch out for that. Together with Dimo and Desmond, now they are in Frankfurt with the new 70, they are getting T1 weighted images in collaboration with the Bonn guys, as far as I know. And there, of course, some challenges to deal with the noise, and we are looking into some ways of denoising this single contrast image that is at 0.35 millimeter isotropic whole brain again. Of course, Renzo, you know him, and Alessandra, they are looking at MGH using the MGH data. 0.4 millimeter fMRI, also 0.8 millimeter fMRI, and in combination with, again, the 0.35 millimeter T2 star weighted imaging, the meso-veins anatomy imaging. So we can overlay all these images on top of each other, even though with partial coverage. Like we figured all these pipelines and looking at the signal behavior between different arteries, veins, and cortical gray matter, and so forth. And at the same time, actually, Sebastian Drespa had a data set from a few years ago that is not as fancy as this one. That was a kind of standard VASO, 0.8 millimeter, I think, together with the GRE imaging, not 3D EPI. But he's also there, has a very good data set that now together with him, we are looking into, again, how the arteries and veins behave across different stimulus durations. So he had a varying duration stimulus, and just to see the HRF shape and how they differ and so forth. And last, together with Saskia and Marshall, we are looking at segmenting all these veins to later hopefully do more useful analysis to extract some maybe vascular, like tree diagrams, and see how things are changing when you go up and down in the vascular tree from the capillaries to mesoveins and mesoveins to macroveins and so forth. And that involves mesoveins together with the time of flight imaging and so forth. So I think Marshall also had a ISMRM abstract. Okay, so this is the end or the beginning, as I would like to say, because I just want to make a very strong point at the end of this talk. This is not like a one-off thing that I am able to do only in Maastricht. Like since last year, we are successfully getting similar data set in all across the world. That at NIH, Renzo got some before he came to Boston. In Brisbane with Saskia, we get really good quality data again. These are all set up like without me, right? Like people kind of went there and set it up with 3D EPI and so forth. Of course, in Paris recently through Rudy, I got some data and looked at the leptomeningeal situation there at 11.70. You get like really good contrast because the venous signal dies down even quickly, right? And it gives like an even higher contrast to noise there when you look at the veins. So the veins even pop up further, even at the same resolution at 11.7. In Frankfurt with Dimo and Bonn, people are just getting it. I believe Renzo is already getting some in Boston now. And there are others lining up to get similar data. I know Toronto is getting it. I think Stanford, with some collaborators in Berkeley, they set up like a single echo version of it. So this is like happening. And I am happy about it because it means that like this just, I feel like this is the new regime. You know, we just need to get used to it. Like whole brain, 0.35 millimeter T2 star imaging, and I believe T1 will come very soon as well, is there. We can do it in 7 minutes, and we can do it very nicely at 70, especially T2 star weighted imaging, because we have the very good contrast from the venous decay being fast. And like this is like never before done, right? I hope it is clear. Like now we can put a person inside in 7 minutes. We can get the resolution of their veins down to the intracortical like sticks that go inside. Like this is to me crazy, right? And yet alone, I didn't even go into the subcortex yet, which I think we need to, and cerebellum, right? There is all these different vascular configurations there as well, and how it affects the activity in hippocampus, in thalamus, LGN, cerebellum. These are all now ready to be investigated by using this mesoveins imaging. And with that, I would like to say thank you. That's my talk.
Thank you, Faruk, for this nice presentation. That's really cool. Are there any questions already from the audience? Maybe I start then. So you, specifically on one of the last slides, you do see that kind of when you look at the brain from the bottom, it's kind of brighter than kind of when you look at it from the top. So maybe I'm asking you kind of what are the remaining sequence challenges that you would want people to work on to kind of reduce the limitations that these methods have, or what are the limitations, like with respect to EPI, right? What do you lose going to EPI? Yes, you are much more efficient, you're super fast, but are you having more kind of phase wraparounds? Are you having kind of within voxel dephasing? And yeah, what is,
So,
yeah. Right.
Yeah, I see. Actually, maybe I didn't show, I forgot to show, but of course, the inferior part of these mesoveins images are not so nice, like the inferior, superior, inferior anterior part of the temporal cortex, the usual suspect areas, right? Or orbitofrontal cortex. By having like more coil elements to kind of increase your SNR and having like a better shimming, getting data better there, I think would help anyone, right? Not only anatomy, but fMRI as well.
And is that a thing that is EPI specific, or do you see that in the GRE flash-based multi-echo as well?
I see it in all of them. It's not so much EPI, but like this EPI specific statement, like it is to me all about the readout duration. When we are talking about fMRI EPI, that is like very long readout, right? 60 milliseconds, let's say. This is like very long to stay there. And when all these geometric distortions are happening, like the signal is dying down and you are mixing like the early part of the case space with the later part of the case space, going through it, like mixing all, making a soup. That is giving rise to all these bad distortions. And of course, by using multi-echo and multi-shot that enables you to do multi-echo, cutting the readout duration short is like a very big advantage to me, because you really then approach to the GRE regime or flash regime that is like kind of quote unquote distortion free, right? And that is to me like a big deal, especially around the veins. Also, like I see that when I'm in a very long readout time, there's more distortion, of course. Then whatever you do, the image doesn't look so nice. So like getting a good image while shortening the readout, I think is the most important way to go. Like if there was a multi-echo, 0.4 millimeter fMRI, I would do it immediately, and I think everything would look nicer there. But there are of course like other challenges with that. Oh, the other limitation, actually, funnily, is the reconstruction PC. Like, we cannot go fast enough. Like, we can try other like fascinating things, right? But it just keep crashing. And of course, the moment you say offline reconstruction is needed, nobody will use your sequence. Like, nobody will come in night and reconstruct, at least like average speaking. That's why I pay a lot of attention to kind of just create things that can just work in the scanner as it is, right? You don't need to have like a separate recon package or expertise and things like that. Did I answer nicely? I don't know.
Yes. We have a question from Andrada Triaba. She says, or maybe you can see it. Did you look into whether venous variations are related to handedness of the subjects? And
Yeah,
I
no,
forgot to mention, excellent talk. Yeah, I didn't want to
yeah,
cut it.
thank you. I didn't. And I think this is just the beginning of looking at these things. And I can imagine that it's a bit of a stretch to say that like the configuration of the veins determine your cognitive abilities or something like that, right? This sounds a bit like too much to me. Uh, but I don't know. I didn't look at the data in that way, so who knows? That would be like a strange world, I guess, if that's the case. But yeah, who knows? Like if there's I mean, I always think like this. Maybe it's naive, but when you build muscle, right, they become more vascularized and so forth. If you use like one part of the brain too much, I guess it becomes more vascularized as well, right? Maybe. So maybe in that way there is like some connection between cognition and vascular geometry, but at this point I don't know.
Are there any other questions? Did you look at the phase as well of those data?
Oh yes, I did. Yeah, no, the phase is good. Like there is information in the phase that can be pulled out as well. Actually, this is one of the other directions. I should work on it a bit more. Like when we really need to do one run, like some people are really limited in time, right? They can only afford 7 minutes. Of course, then it becomes a bit for looking at the veins. I would say 7 minutes of good data is enough. Like there is good enough contrast, and it's really like. But if you are looking at other details like laminar variations and so forth, you need more. Like you need more SNR, and maybe like bringing the phase data there in a single run limitation could be a way to enhance the single run SNR a bit further.
You see the question, right, from Charles Jennings.
Hi, I can just ask it if you can hear me. Thank you very much. It's very interesting.
Yes.
I was asking whether you've seen any variation by either by age or by sex. I don't know if you've gotten to that point yet.
But I didn't get into that point. But these are all the things that I think collectively we should all look at. Like, I mean, these like people who study arteries and veins, they always say that like arteries become more stiff over age and so forth. But I don't know to which degree we can pull that information from the data. Like, is it like is the relevant scale the microscopic scale? Then I cannot reach, right? Because I'm at the mesoscopic. But maybe in the mesoscopic scale, let's say that maybe one area becomes more densely populated with veins or less dense over age, right? With this intracortical. That might be interesting to look at. But I don't think anybody knows. Like nobody knows whether this is relevant or not. That's why I find it exciting. Like it might be just irrelevant, right? Maybe we just need to go to microscopic scale. But nobody reached mesoscopic whole brain anyway. So it might be valuable to just look into it.
Great, thank you.
I'm embarrassed to say I missed one question. Kiang Liu, do you want to ask it yourself?
Yeah, I will also ask. We are very interested in this sequence, so I wonder if this sequence available sequence on the, for example, the 70 or like any scanners at Brigham, or it is working in progress sequence.
I can answer that. I think yes, both. The protocol has been installed on. Actually, the sequence has been installed on both 70 scanners, Bay 2 and in Brigham Women. It has been extensively tested already and validated on in Bay 2, specifically also with the 64-channel call, which boosts the SNR a bit without running into recon issues yet. On the Brigham Women scanner, it is installed. However, we haven't tested it yet in vivo because we had IRB issues. But IRB is approved since last week, like the week before, so we can test it soon. But it is there, yes. It's I think a C2P. It's not a VIP. It's not a Siemens VIP.
Thank you so much.
All right. If there's no further question, we are almost at the hour. So thank you, Faruk. And we meet again in 2 weeks when Alejandro Moreal will talk about spiral fMRI at 11.7, 9.4, and 70 with laser. So, all right. Thanks.
Bye.
Thanks, Brian.